Greetings. If you're watching this video, I assume it is because you are trying to get some points. So to get those points, I'm going to do things as I usually do. Throughout the lecture, I'm going to give some random attendance words. I might say them, I might circle them on the screen, I might point to them. But anyway, throughout the lecture, I'm going to give some random set of words. And when I do that, you're going to write those words down and take a screenshot when I say those words. And then at the end of the video, you're going to send me an email. That email is going to include a list of those words with the accompanying screenshots. In addition to, the last thing you'll need to do is send me one question about the material covered in this lecture. The first word for attendance today for you guys, for those of you watching the video, will be mirror. You know, like you look at yourself in the mirror. A mirror is the first word for attendance. That out of the way, it is about 7:25 right now. So you can skip ahead about 30 minutes into the video, and that's when things should get started.
Morning.
Got you marked down present. But it'll be just like Wednesday, where even though I have you marked down present, you still have to send emails to get the points today.
Okay. How on the pre-lab, how do you like upload the image of the or the screenshot?
I'll show you.
Because I have all the questions done, I just can't figure out how to get them like onto the pre-lab.
All right, let's see here. Good question. And this is recording, so hopefully this can help somebody else out. Let's see here. Let's see. All right, so you've already done these quizzes, right?
Yeah.
All right, so after you hit click score, you may have already done this, but I'm recording, so I'm gonna say it anyway. You can see I hit click score, and I can see the score right there is 4 out of 13. Of course, no, you wouldn't get any credit for that, but this is just an example. There we go, 4 out of 13, and I also have my name and that. So this is what the screenshot should entail, right? The score in that first question has your name, and of course the section number. And of course, we were in section 2. Not section 3, that was just an example. So let's say you have that, and now you're ready to upload it. Just where it says insert screenshot here, just highlight it, and then go up here to insert, image, upload to the computer. That's that.
Gotcha.
Like so, there's an image of an onion root from the microscope. But yeah, that's it.
Thank you.
You're welcome. And I know I just told you, but when it comes time for you to do it, if you forgot what I said, let me know.
Okay.
Don't mind repeating myself.
You think we're gonna get all this snow?
I guess so. I've never, I shouldn't say never. I rarely see them this confident about it. What do you think?
I hope. I like snow.
I don't mind looking at it.
Yeah.
I used to love it because, I'm from farther south, so
Oh yeah.
it was always new to me. I never got to see it.
Mhm.
So when I first moved here, I was like, cool, snow. I just got kids, and that means I'm just stuck with bored kids. It's tough.
Yeah.
Especially if the power goes out.
Mm-hmm.
Because then, yeah, we can go out and play, but that only lasts so long, and they get cold when they come in. Sometimes they can read a book or play toys, but eventually they're going to want to watch something, or I'm going to want to listen to music. It's tough. Where do you live?
Cross Lanes.
Okay.
So we're just right over the mountain.
Yeah. Yeah, we'll probably be spending, I don't know. We might go to my in-laws in Poca because they have a generator.
Yeah, my grandma does. She lives in Poca too.
Yeah.
A lot of people down there, I think, do because their power goes out a lot.
Yeah. Yeah, the problem is they live up a hill. So we just have to decide if we're gonna go. We need to go probably Saturday, just stay before that starts snowing, because they'll probably be snowed in and we can't get to them after that. Tough situation.
Yeah.
You know when they're supposed to be done with all that work, the road work and cross lanes?
No clue. They've been working on it for so long.
It's miserable.
I know they finally opened up the one lane, but they're still apparently doing more. I don't even know. I don't know what all they're doing.
Can't stand going cross lanes.
Yeah.
Morning. For that
Morning.
reason.
Yeah.
Lucas is here. We're gonna do the same thing we did yesterday, Lucas, where at the end of the lecture, you'll just send me an email that says, I was here to get your points.
All right.
And of course, as usual, you can also send the words and the question for extra credit.
Yep.
So Barrett, were you the one that was that I was emailing with about the screenshot thing, or was that someone else?
I don't think that was me. No.
Okay, was that you then maybe?
The one about submitting the lab?
No, but that's something too, okay.
Yeah,
Yeah, I'll have to figure that out. So the screenshot you sent me for that was from your phone though, right?
it was.
I really think that's the issue. I mean, I don't know for sure. So we need to get you to a computer. And I know you may have done it on your phone, but since it's a Google Doc, once you're on the computer, you should be able to log into it.
I
Find it.
talked to Isaiah about it last night.
Okay.
He sits right over here with me, but
Yeah.
he was able to get it in the Bravo side.
That must be it, yeah. Because there is a delete.
Probably.
There's a delete button. I
That
don't know what it looks
was,
like.
that was a few hours after we.
Huh. Okay.
Oh, yeah.
Well, I'll be there for office hours if you want to take a look.
Okay.
I have to see if I can get my hands on the computer. The better thing, let me think about that actually, because that computer that you used on Wednesday should have been turned back in by the TA that it may not have. So it might still be in my office, in which case we can just knock this out right after class.
Okay.
But if it has been turned in, that means I don't have a computer for you, which means if you can, between now or then and 10 o'clock before, well, actually anytime today. If you can get in front of a computer and then we can meet online, that would actually be better because you can share your screen and I can talk you through it. Otherwise, you know, if we do it in person, you'll have your computer and I'll just be looking over your shoulder, which, you know, works, but not always ideal. Savannah, right? And where are you from again? I'm sorry.
I'm from here, from Charleston.
Charleston. And again, I'm sorry if I've asked that before, but
You're fine.
eventually I'll remember these things. We got Cross Lanes, Charleston, and I probably, hold on, now I've asked you, I'm gonna, Boone County?
Fireworks first.
Sweet. Good morning. So, is it Ashley? No. You're Ashley? Okay, I was close though. I was blaming on my bad eyesight. Well, no, I was actually trying to point at you. Is the lie I'm gonna tell. Let's see. Hannah?
Yeah.
Yes, all right. Got it.
Do I?
Well,
Haley?
yeah.
Today?
You didn't know what? Yeah, wow, one, three, two.
Is it Katie?
Yeah.
All right. I'm getting it. So far, everybody's accounted for, yes. So anyway, we got Cross Lanes, Charleston, Boone County. I'm gonna be asking this a lot, sorry. Eventually I'll remember. Where are you from again?
Who, me?
Yeah,
Cross Lanes.
I've got two Cross Laners. Actually, what do you call somebody from Cross Lanes? Cross Lanians? Stuck in traffic?
Oh,
What about you? Where are you from again?
Nitro.
Nitro. Good. So this is very, you guys are a very close group geographically. Let's see. So it's Schaefer, correct? All right. Trahan, Inca, and of all the people, I've been talking, I'm trying to remember where everybody's from. Of all the people, I should remember where you're from because it's not here. It wasn't Iceland, was it?
Finland.
Finland? Okay. Are your people back home saying anything about our movement on Iceland? Is that a topic of conversation? Since it's a NATO area.
oh yeah. They're always talking about what's going on here.
I imagine. All right, let's see. We've got Isaiah, correct?
His favorite thing is that
From the Tampa area.
that's hilarious. He tries to do it himself and he just goes.
Edwards, is it? Yeah. And where are you from? Charleston. Charleston? Hey, so Savannah. Hey, you guys have that in common. It'd be easier if you were from Savannah. That's where I'm from. That's where I was born. So
Yeah, I don't get it.
I was born in Savannah, but I never really, I don't have any memories. But I was stationed in Beaufort, South Carolina, so I hung out a lot in Savannah as an adult. All right, let's see. Oh, shoot, it's 8. I guess I won't guess. Let's just do attendance. Here we go. Attendance.
I don't know.
Sherwin is here. Van Camp is here. Wooten is not here. Trahan is here. Dickens is here. Clark is here. Inca is here. Isaiah is here. Copes. Copes is not here. Smith is not here. Watson is here. Kaylee? Kaylee is not here. Lucas is here. Marley is here. Noah, correct? Noah is here. Savannah is here. Nia? Yep, Nia is here. Edwards is here. And that's everybody. Did I miss anybody? All right, let's get started. We're gonna do attendance the same way we did Wednesday. Like I said, I'm gonna change it up throughout the semester, just to keep you guys on your toes, because the point is to make sure you're paying attention, right? So today, we'll do what we did on Wednesday, which is you're gonna send me an email at the end of this, sometime before 9 a.m. and say, I was present, and that's it, and to get your point. Now, if you want to, you can do what the people watching the video are required to do, which is also send me a list of the attendance words that I give throughout this lecture for extra credit, and also, or if you ask me one question about the material covered in this lecture, you will also get extra credit. So all those things you can get extra points for, but at the very least, you need to send me an email just saying, hey, I was here. And again, if you're watching the video, you're gonna do the screenshots every time I say an attendance word, and you can send those along with the question. That's all mandatory for the video. Anyway, really quickly with the course announcements, like I keep saying, I know I'm beating a dead horse, so I really want to make sure you guys know, especially given the weather that's coming in. Make sure you check your course announcements and your emails before you come in, because I'm willing to bet that either I can't make it in, you can't make it in, or campus will be closed on Monday, right? So if that happens, there'll be an email, and I'll say, here's the link, meet me online. And we'll just do our lecture online. So you can do it from the comfort of your bed or whatever. So any questions about that? Group emails, I just thought about this. So a lot of times when I do emails, I do a lot of copying and pasting, not just emails, but a lot of times too with like feedback. I'll copy it and paste it, and I'll just make little edits. Like when I give you your feedback on your lab, I copied it from someone else, I pasted it to the thing, and then I changed it to be like yours. But sometimes I mess up. So if anything ever doesn't make sense, like in my feedback, or if you get an email, that's probably why. So just let me know if something doesn't make sense, and I'll clear it up for you. For example, there's one person who's out because they're having a family emergency, but I will send sometimes, and you may have gotten like a group email for, like, if you're receiving this email, it's because you were absent, and here's what you need to do to make up for your points, right? In that case, that person, I'd already talked to that person. So I kind of felt bad afterwards, like, oh yeah, I've already talked to them. And I'm beating a dead horse, and they've got other things to deal with. So again, if you get something like that, I apologize in advance. Any questions about that? All right. Lab 1 is due today, pre-lab 2 is due today, sometime before midnight. You don't have to do any of it alone. I'm willing to help, I'm not willing. I'm excited to help you. I'd rather help you than have you do it alone. So let me know, I'll meet you online to help you. What to say about that? Oh yeah, I'm not doing this to be picky. Trust me, I've been doing this for a long time. I do this to help you. You're gonna wanna save your files as a PDF before you upload them. That's a big deal. And also, these are not designed for tablets or phones. You can make it work, so be it, I guess, but you really want to do those on computers, in my opinion. I'm not going to tell you if you have to, but it will probably really help. So anyway, any questions about that? You guys are nice and easy. Speaking of which, like I said, I'm here to help. Those are my office hours. I've mentioned them before. I'm mentioning it again today. I'll be in my office and online until 10 a.m. At that point, I'll probably leave and go home and work from home, but then I'll be back online. So again, I'm here to help you all day, but you're guaranteed to find me in the office and online until 10 a.m. today. Any questions about office hours? All right, we already talked about participation and grades and attendance and all that. The first word for attendance is John Hancock, because today is his birthday. John Hancock. All right, so any questions? Before we get started, do you guys have any kind of announcements? Like you heard any kind of extracurricular thing? We've got a fundraiser going on you want to talk about, or something in your work? No? All right. Well, I got a random one. Here's a random one for you. I collect all kinds of weird things, so I can't offer you extra credit because that would be bribery. But if you guys have like old receipts that are less than 14 days old, feel free to bring them to me. I'll take them. Or I'll share this on Facebook if you want. But I've got like some app where you can take the picture of the receipt. You get a little bit of money back for it. So if you want that app, it's free, and I'll share it to you. Otherwise, I'll be glad to take your receipts and your change, basically. Does anybody else have anything random like that you want to share that we can bring to you? I collect all kinds of random stuff. Old key cards, like or not credit cards, but like hotel keys. I've got a little puncher, and I turn those into guitar picks. So I'll also take those if you don't want to throw those away. Anyway, let's get back to it. Let's talk about this. All right, so first of all, before we jump into this, how many of you took biology because you didn't want to take chemistry, but you had to have science? Oh, there's a few of you. Okay. Well, the bad news is we're doing chemistry. The good news is It's easier than regular chemistry. How many of you guys have had chemistry before? Okay, that's good. So this will probably be easy compared to what you learned. We're not gonna be balancing equations or anything like that. How many of you actually have had biology before, like in high school or something like that? Okay, so then you've probably already been exposed to this chemistry. So I'm sorry if this is boring to you, some of this might be a review. Anyway, like I mentioned before, some of these, or a lot of these PowerPoints are based on the old textbook, so I left things in it from the old textbook, including this, because the beginning of the old textbook, the beginning of each chapter of the old textbook has like a little thing saying, why does this chapter matter to your everyday life? So we'll talk about that a little bit. Of course, this probably doesn't matter to your everyday life, but it would for me, because I'm from Florida. But anyways, anybody know what this is? That was kind of a hint when I talked about being from Florida. Anybody know what that's a picture of? Yeah, it's a coral reef. I think that someone said reef, I think. Yes, it's a reef. Can anybody tell what's wrong with it? Probably not. It's really hard, bad picture anyway. Anyway, this is a dead piece of coral. And the way the old textbook wrote it, the caption reads, "The exhaust released by a car in Boston contributes to the death of coral in the Great Barrier Reef of Australia," which is a true statement. And I think would be a different, more relevant way to say it, for me anyway, would be the exhaust released from John Amos power plant kills coral in the Florida Keys, which is relevant for me because, again, I live here and I'm using that electricity. But I also am from the Florida Keys, so that does affect where I'm from. Anyway, what's this? That's an easy one. What's this a picture of? French fries. And what's that being poured on it? Probably salt, right? I mean, technically it could be white powder, but I would assume, yes, it is table salt. And we'll get into that later. Not just salt, but table salt, because there's all kinds of different salts. But this is an interesting thing, I think. Table salt's a very interesting thing because it's made, does anybody know what it's made of? The two elements that it's made of? Not that you have to, just curious. No?
NaCl.
Yeah, NaCl, which is sodium chloride. And the reason I find that so interesting is because sodium is an explosive metal. So if you get sodium wet, it explodes. Chloride is what we use to make chlorine gas, which is a chemical poison that was used in war. So you have an explosive metal and a poisonous gas, and together it makes a delicious salt, which also is good for, well, not good for you. Like too much salt is bad. So there's a few things I want to get at before we move forward. That's very important here. When we're talking about chemistry, a lot of people try to scare you with the ingredients. Oh, you're eating that, you realize it has this in it. Oh, that has that in it. And they'll try to scare you because they don't know, most people just don't know enough about chemistry. So think about it. That could be scary if we talked about salt. Like, oh my God, that's, if you didn't know about salt, someone could be like, oh man, you're eating that? You know that sodium is an explosive metal, right? Or you know that chlorine is a poisonous gas. And those would be true statements. But when you put them together, they're perfectly fine for you. Which brings me to my second point. We know, again, salt not only is perfectly fine for you, but you need it. But on the other hand, too much of it is poison, is bad for you, right? So that's another point that I'm going to be hammering throughout this chapter. The dose makes the poison. So a lot of people will say something like, oh, you shouldn't drink that. That's got this in it, and that's a poison. And yes, anything is a poison if you have enough of it in the right amount of time, pretty much. You know, even oxygen, which we need to live, in some ways, is doing bad things to your body, which is why you're supposed to eat antioxidants, because it helps to repair the damage that oxygen does, right? So everything is a poison, basically. So don't let people scare you by saying, "Ooh, that's poisonous." Your question should be, all right, well, how much of it is poisonous? Anyway, and then finally, this is really not interesting at all, but your textbook, the old textbook included that picture. Anybody want to guess what kind of metal that is?
Copper.
Yeah, copper. Anyway, really irrelevant, but yeah, that's copper. I guess you could steal it and make a lot of money, and some people do that. Anyway, this chapter is broken down into 3 sections. The first part is the building blocks and molecules. Then we're going to talk about water. Then we're going to talk about biological molecules. So let's jump into it. I'm sorry, this is hard to read. The first part, 2.1, here's our learning objectives. Wow, yeah, I can't even read that. So luckily, the learning objectives aren't that important. But anyway, they are described, by the end of this, you should be able to describe matter and elements. And you should be able to describe the interrelationship between protons, neutrons, and electrons, and the ways in which the electrons can be donated or shared between the atoms. So that's our learning objective. Speaking of atoms, does anybody know what an atom is? If a kindergartner asked you what it, well, that might be a little bit too hard. If a fifth grader asked you what an atom was, what would you answer? Like, how would you describe it? Just out of curiosity, let's see what you guys know already. And some of you are elementary education majors, so this is directed towards you. Now's your moment to shine. How would you describe an atom? Nothing? All right. Like I said at the beginning of the semester, I'd rather have a conversation than talk at you, but it doesn't always work. So each element, and we'll talk about what an element is a little bit later, but each element consists of one kind of atom. And an atom is the smallest component of an element that retains all of the chemical properties of that element. So that's what you need to know for the exam. You need to know what an atom is. And as usual, I'll remind you, sometimes it'll be verbatim, like in this multiple choice exam. You might get that written just like that, or sometimes you just need to know the gist of it. So I don't necessarily want you just memorizing words and being able to regurgitate them. Just make sure you understand what they are, yeah. Smallest component of an element. So it doesn't get any smaller than that. It does, but if it did get smaller than that, then it would no longer retain all the chemical properties of that element. For example, in that picture what we have there, not that you need to know this, but it's helium, and I know it's helium because it has 2 protons, and I've just been teaching this forever. Now, we could technically break that down a little bit more. If I were to get rid of one of those protons, that thing would no longer be helium though, and we'll learn about that later. This is just an example, you don't even know that yet. So again, if I take away a proton, I've changed the element. It went from helium to hydrogen because I took away a proton. So again, I'm just reiterating this fact right here. That yes, you can break it down into smaller pieces, but at that point, it would no longer retain all the chemical properties, right? In that example that I just gave, if we got rid of the proton, it would no longer be that element, it would be a different element. Likewise, if I were to add a proton, it would no longer be helium, it would be a different element. So any questions about what an atom is? Okay, but like I said, there are smaller parts that make up an atom, and you also need to know those. This is those. Protons, electrons, and neutrons. You need to know them. The order that I just spouted those out doesn't matter what order. You could say neutrons, electrons, protons, neutrons, whatever. You don't need to know that in that order, but you do need to know their charge and their mass. Proton has a positive charge. And that, in my opinion, should be easy to memorize because pro, positive. It's an alliteration. We both start with P. Electrons have a negative charge. That should be easy to remember. 2 ways. First of all, even though we haven't talked about it yet, neutrons, obviously that's easy to memorize. That's neutral. Neutron, neutral, right? So proton and neutron, that's kind of in the word. So then by definition, or not definition, excuse me, by process of elimination, you must know that electrons are negative. And if all that fails, just imagine getting electrocuted. That would be a negative experience, right? So that's another way to help you remember that electrons are negative. Now, the other important thing is the mass. Protons and neutrons both have a mass of 1. As far as we are concerned, electrons do not have mass. Like I said, as far as we are concerned. For extra credit, don't do it now. Pay attention to this lecture now, please. But anytime, maybe this weekend, instead of having fun in the snow, I'm sure you're going to be doing this instead. Look up what is the mass of an electron. Wouldn't that be exciting? So much more fun than enjoying your weekend, right? Spend all your time doing that. But anyway, if you do send me an email saying, I looked it up, and according to this source, include your link, the mass of an electron is blank. But again, for this 100 level course, we're just going to assume electrons have no mass. So any questions about the 3 different subatomic particles? All right, another thing you can look up for extra credit, because we don't even get into this. I don't think your textbook touches this. These things are made up of smaller parts. Protons are actually made up of different parts. Neutrons are made up of smaller parts. We don't even talk about that. It gets really complicated, but you can look it up if you want for extra credit. Anyway, this is where we get a little bit of math in here. Some of your questions, this next point is going to be the inspiration for some questions you're going to get on the exam. This is one of those few questions we actually do a little problem solving instead of just remembering something. If the number of protons equals the number of electrons, then that means the net electrical charge is 0, which means the atom is neutral. So far, that's probably seems pretty easy, right? But where people get confused is when we start leaving this idea of 0. And we're going to talk about this in another slide, but really quickly, I'll just introduce you to this idea before we talk about it later. But say, for example, you have this hydrogen, right? This hydrogen has 1 proton, 1 electron, it's neutral. Now, if you were to add an electron to it, it would then become negative. And for some reason, that confuses people. I think it's because the idea of when you add something to it, your brain thinks add, positive, plus. But remember, when we're talking about when you add something negative to something, it becomes negative. Does that make sense? Likewise, if I were to take away an electron, it would become positive. So don't let that trip you up. It's very important that you remember electrons are negative. Therefore, if you take them away, something's going to become positive, and if you add them, something's going to become negative. But again, we'll formally talk about that later today, hopefully. So any questions about this slide before we move forward? Okay. Really quickly, this is just an example. Hydrogen, gold, you don't need to know anything about that. The point is both of these are neutral. 1 proton, 1 electron. 79 protons, 79 electrons. They're not charged, they're neutral atoms. All right, so another thing you need to know about protons, electrons, and neutrons is where they are. For example, protons and neutrons are inside the nucleus. Electrons are outside of the nucleus. It's just that simple. I'm using uranium here as an example. You do not need to know anything about uranium. But yes, you definitely need to know protons and neutrons are in the nucleus, electrons on the outside. One thing you don't have to know, but I find interesting, so I'm going to bring it up, is think about this. Protons are positively charged, right? And what happens when you put 2 things together that have the same charge? Like 2 positive things or 2 negative things. What do? Do they attract each other? Do they repel each other? Or is it just no relationship at all? 2, in this case, 2 positive things. When you put 2 positive things together, what do? Attract, repel, or neither. Think about a magnet. North and north, when you try to put that together, or south and south, what happens? Attract, repel, or negative, or neutral? Repel, right? They repel each other. So think about this. And again, this is not that important for biology, but I find it slightly interesting. This this uranium nucleus, not that this number's up there, but I happen to know, has 92 protons. 92 things that don't want to be together that are stuck really close together. Imagine how much energy it takes to squeeze those things together. And this is why we use uranium for bombs and nuclear power. Because once you break those bonds, like the stuff that keeps them together, however much energy is there keeping it together, once you break it, that energy is released. It's atomic bombs. Now again, for this class, that's not important. But that concept will come out back throughout the semester, at least the first half of the semester, or that theme, excuse me. The idea of when you build something, however much energy is holding that thing together, that's how much energy will be released when you break it. And later, we're going to talk about molecules, which are atoms coming together, right? And all the energy it takes to build those molecules, that energy will be released when you break those molecules. So that will be important. We're never going to talk about protons, like nucleus, breaking up, but we will talk about other things breaking up. So anyway, for the exam, again, the important thing about this slide is that in the nucleus you find protons and neutrons. Outside the nucleus you find electrons. So any questions about that? All right, here's another picture demonstrating the same thing. There's a nucleus that has protons and neutrons in it, and then the electrons are on the outside. I like this picture. I don't remember if it's from your textbook or the one before it, but it's a good one. We're not going to look, when we talk about electrons later, probably you're always going to see rings like that. And those rings are very helpful for this level of chemistry, because that's going to help us, well, you'll see why later. But that helps us keep track of things that in real life, they're not actually orbiting in rings like planets around the sun. In real life, it's more like a cloud, meaning they're just likely to be somewhere in this cloud at any given moment. For the exam, that's unimportant. I just wanted you to know in real life, it's more like this than what I'm about to teach you. What I'm about to teach you is those rings. And those rings are useful, but it's not very representative of real life. Anyway, any questions about this slide? All right. Again, we're still talking about atoms. Let's talk about the structure of atoms. Atoms of an element have a unique number of protons. You definitely need to know that. Another way of saying that is the number of protons defines the element. Another way of saying that is if you change the number of protons, you change the element. So an element has an atomic number, and that is how many protons it has. So I told you that uranium had an atomic number of 92. Not that you needed to know that, which that means it has 92 protons. Actually, I take that back. I told you it had 92 protons. Therefore, its atomic number is 92. Helium, which is the example that's up here, right? Its atomic number is 2. Therefore, it has 2 protons. Oxygen, it has 8 protons. Therefore, its atomic number is 8. You do not need to memorize any atomic numbers in this course. No, at no point am I going to give you some element and say, what is its atomic number? Unless I give it to you like this. I might ask you to decipher something. I might give you this. I'm like, all right, what is helium's atomic number? Like I might give you this picture without the arrows pointing at it and say, what is helium's atomic number? Oh yeah, it's 2. But again, you do not need to memorize any symbols. You do not need to memorize anything about the elements. If there's any questions about elements, you'll either be given the pertinent information or a periodic table or a picture like this. So yeah, again, helium is just an example. 2 protons, therefore its atomic number is 2. No other element has 2 protons, by definition. If you were to add an element, add a proton, it's no longer helium, lithium. If you take away a proton, it is no longer helium, it's oxygen. Again, I just said oxygen, good grief. Hydrogen. Still haven't had all caffeine yet. Anyway, yes, so make sure you know that. The atomic number defines the element. If you change the number of protons, you change the element. Any questions about the atomic number? The next one is also pretty simple, and you're going to get at least 1 or 2 questions about this on the exam. These are going to be one of those figure it out questions. The mass number. That's simply the number of the protons and the neutrons. So the question you're going to get would be something like, I might say, using this as an example, I might say something like, helium has an atomic number of 2 and a mass number of 4. How many neutrons does it have? So then you'd have to think, all right, its mass number is 4, and the mass number is protons plus neutrons. And you said the atomic number is 2, therefore it has 2 protons. So 2 plus what equals 4? 2 plus 2 equals 4. Right, so you're going to have a very simple math question like that. It'll be simple enough where you will not need a calculator, which will be important because you'll be doing the exam here, so I can see you. And if you pull out your phone, for all I know, you're looking up something on ChatGPT to look up an answer. So don't do that. Again, if you feel like you're going to need a calculator, bring one or tell me, and maybe I can bring you one. You can't use your phone's calculator when you're doing an exam. Anyway, yes, so you're going to get a basic question like that. Again, I'll write it down like this very quickly before we move forward. Just think about it almost like algebra, right? So we're going to have, the protons plus neutrons equals the mass number. Just do it like that. I'm just abbreviating. So just think about all the different questions you could ask, right? So I could give you as long as I'm giving you 2, then you'll have to figure out the third, right? So I might say something has this many protons and this many neutrons, and then you have to figure out what its mass number is. Or I might say it has this many protons. This is the mass number. How many neutrons does it have? Or I might say it has this many neutrons. This is the mass number. How many protons does it have? Does that make sense? Nice, simple math. And again, you don't have to memorize this. So don't feel like you just need to study the periodic table. And then when I ask you what's the mass number of this element, you're like, oh, I remember that one. That's not the point here. The point is for you to be able to figure it out. Anyway, so no questions about that? All right. This gets a little bit more complicated, and your textbook doesn't really talk about it. So that's the mass number. Nice and simple, right? The mass number, 4. But notice this. This is something different. Then I said this has the atomic mass of 4.003. So what's the difference? Why is the mass number 4, but the atomic mass is 4.003? Why does that make sense? Well, the atomic mass is different than the mass number. It's similar, but different. Basically, it represents an average, and hydrogen's a great example. Isaiah, you're in the back. Can you look up at the top left of that periodic table and tell us the atomic mass of hydrogen at the very top left? Oh, yeah, actually, it's right there, sorry. Yeah, so this one's a little bit more precise than that one. 1.008 is what that periodic says, periodic table, which is rounded up. It's actually 1.00784. But here's what this means. There's not a single, and again, hydrogen is just an example. You do not need to memorize this. There's not a single hydrogen atom out there that has this mass. Nothing weighs this much, 1.00784, because these are whole numbers, right? You do 1 proton, 1 neutron. There is no fractions. There are no decimals. But it's an average. So this is not very important for this 100 level course. I'll go ahead and explain it anyway, just so you know what it means. What this number tells me, since it's an average and it's really, really close to 1, that tells me that most hydrogens in the universe weigh 1, right? Like this one, 1 proton just weighs 1. But there are some other hydrogens out there that have a neutron. And there's even fewer out there that have 2 neutrons, so an atomic mass of 2, an atomic mass of 3. So if you were to take all the hydrogens out in the world or in the universe and weigh them and divide them by however many there are, you would get this number. So that's the difference between the atomic mass and the mass number. The atomic mass, again, is an average. And again, for this 100 level course, that's not very important, but now you know what it means. Again, there is nothing that weighs this. They all either weigh 1 or 2 or 3. When you average them all, that's what you get. Does that make sense? All right. Any questions about that? Really quickly, let's talk about periodic table of elements. You will always be provided with a periodic table of elements when you need it. And that will be rare because we're not going to do much that's going to require a periodic table of elements. But it includes the atomic number and the atomic mass of every element that we know of. That's what it does. It also provides key information about properties of elements, which we won't even get into in this class. It also shows how electrons are organized. So we're going to talk about that later, hopefully today. But even then, we're still not going to use the periodic table to do that. I mean, we might start with that, but we won't finish. It provides important details about how atoms will react with each other. Yeah, that's it. Sorry, I should have said this when I started. I see people taking notes. There's no need to write any of this down. I'm not going to ask you any questions about the periodic table. I'm just explaining how we're going to use the periodic table in this course. So yeah, there'll be no test questions coming from this slide. It's more like a heads up, like, hey, here's how we're going to use the periodic table. So any questions about that? All right, here's an example. This is what one of them looks like. I'm sure you've seen it before, right? And not that you need to know this, but it's arranged in a certain way. Like I said, it kind of gives people ideas of how things will react. All these, in a sense, react the same way in a chemical reaction because they have the same number of electrons on their outermost shell. These all have the same number of electrons on their outermost shell. So generally speaking, they act the same in chemical reactions. These all, every single one of them, every column, they all have the same number of electrons in their outermost shell. And as you're going to learn later, that really dictates how they react in chemical reactions. But again, I will provide you with a periodic table when we need it. We're not going to need it much. There's nothing to memorize here. So are there any questions about that? All right, next question, next word for attendance. It's written up there. It's a name, actually. Eugene Sullivan. So again, if you're here in person, you don't have to send that list of words, but if you're going to be emailing me anyway, might as well get those extra points. And then later, after we're done, so please don't look now because I'd rather you pay attention to the lecture. But for extra credit, maybe this weekend, again, you have your snow day, it'll be really fun to look this stuff up. Who is Eugene Sullivan? Anyway, let's just say this, it's relevant to this chapter slightly, and it's his birthday. Anyway, isotopes. That's a word you need to know. Before I even talk about isotopes, I want to remind you of something I said about protons. If you change the number of protons, you change the element. Now I'm giving you something different. Isotopes. When I describe an isotope the way I described the last thing, I would say, if you change the number of neutrons, you get an isotope. So again, if you change the number of protons, you get a different element. If you change the number of neutrons, you get an isotope. The thing is, we've already talked about isotopes. I just never called it an isotope. That slide previously that I showed you, where it had a hydrogen with 0 protons, then there was a hydrogen with a hydrogen with a hydrogen with 0 neutrons, then I showed you a hydrogen with 1 neutron, then I showed you a hydrogen with 2 neutrons. Those were all isotopes. They're all hydrogen, but they were isotopes. They were different versions of hydrogen because they had different number of neutrons. So hopefully that's pretty simple. So far, I think that is simple. Unfortunately, later I'm going to give you another word that starts with I, and that's where things might get a little bit confusing because it's a little bit harder to memorize. But anyway, for now, hopefully that's easy, right? Change the number of protons, change the element. Change the number of neutrons, and you get an isotope. What you see there is not from this textbook, that table 2.1 that shows different isotopes of carbon. But I just want to point out, again, this is just an example. I'm not going to ask you any questions about carbon-12. I'm not going to ask you any questions about carbon-13 or carbon-14. I'm not going to ask you any examples of isotopes. The question is going to be, basically, if you change the number of protons, you get blank. And then your choices will be, an isotope, which would be the correct answer, a different element, an ion, which I'm going to teach you later, and then probably some other choice of some garbage that makes no sense. Anyway, any questions about this slide? Okay. Nice and easy, right? Is it? That's a blank slide. I don't know why I have that. Anyway, this is just examples again, right? Carbon. These are isotopes of carbon. You have carbon-12, carbon-13, carbon-14. They all have 6 protons by definition. Its atomic number is 6, so it has to have 6. If you take one away, you don't have carbon anymore. If you add one, you don't have carbon anymore. However, you can change the number of neutrons. Now, knowing this and looking at that, again, I can tell you most carbons in the universe must be this one, because 6 plus 6 is 12, and that number is very close to 12. Yeah, I guess it's not showing here. So this thing's atomic mass would be 12. This one's 13, and this one's 14. But despite that, right, if you were to average all of them in the universe that we know of, we would say it's 12.011, meaning most of them have this weight, 12, not 13, not 14. Any questions about that? Where's going with that? Yeah, sort of like this. This is kind of an interesting way to look at it. I'm kind of going off on a little bit of a tangent, but let me ask you this. What is the average number of fingers per human? Anybody know? The average number of fingers for a human?
10.
I don't know the answer. It's probably not 10 because some people have extra fingers, some people have fewer fingers. I think that particular picture is fake. I don't think anyone has that many extra. But the point is, it's probably not 10, right? Because some people are missing some people have extra. I'm curious to know what it is. You can look it up for extra credit. And also wording, but it's unimportant, so I'm just curious. The point is, right, again, the fact that that's so close to 12, right, well, most carbons must be 12. But yeah, something to think about. What else are we getting out with that? Isotopes, extra fingers. Yeah. Oh yeah, wording is very important too. Now, I worded that question very carefully because if I had said the average human has how many fingers, then I would probably say 10, right? The average human probably has 10. Like, you're average, you have 10, as opposed to the average number of fingers for humans. Sometimes wording can be very careful or very important. Anyway, any questions about this? All right, I'm only gonna mention this really quickly. I'm not gonna test you on it. It's not in your textbook, but it was in my old textbook. So I just kept it on, but why delete it? I might as well teach you. So I'm gonna teach you this, but you don't need to know it. You're not gonna be tested on it. There are something called radioactive isotopes, which are just isotopes, except they're radioactive. And what do I mean by radioactive? It means they're unstable. What does that mean? It means their nucleus decays. So like I was talking about earlier with the uranium, right? All those neutrons or protons squished together. They don't want to be there. That takes a lot of energy to keep them together. So sometimes they just lose protons. Sometimes they lose neutrons. And that's what radioactivity is, when things start losing protons and neutrons, just so you know. Not going to ask you about that, but also this explains carbon dating. I'm not going to ask you any questions about this either, but if you're interested, and I'm sure you've heard of carbon dating, like how do they know this thing is this many years old? This is how. So you can read about it. I'm not going to waste our valuable time explaining it since you don't need to know about it, but there you go. Again, this is from the old textbook, so you won't be able to see it in your textbook, but if you're curious, you can download this PowerPoint and I'll explain it. And there's other ways of dating things. I will also point that out, just really quickly. You know, this carbon dating only works, once you hit 5,730 years, things become different. So you have other forms of dating. Anyway, let's talk about chemical bonds now. This is where it gets a little bit more complicated. This is where we'll have some questions where it's more like troubleshooting or problem solving as opposed to just memorizing something. As far as we're concerned in this class, and this isn't exactly true, but for our purposes, it's only the electrons that are directly involved in chemical reactions. So for us, it's all about the electrons. Specifically, the number of electrons tells us a lot about how it's going to react, or in some cases, not react. Number of electrons determines the chemical properties. More specifically, the outermost ring of electrons is what's important to us. That being said, here's something else you need to know. I wish I had a picture. I'll just draw one. I'm sure you've seen it before. Like I said, we're going to be doing rings. Remember that I showed you that one picture that had the cloud with the electrons? I said that's more realistic. But in this class, we're going to do rings. So yeah, we'll have an inner ring, and then an outer ring, and it just goes and goes and goes. For our 100 level non-biology major class, as far as we're concerned, the first ring holds 2 electrons, and every other ring after that holds 8. Now that's not necessarily true, but for the purposes of figuring out some of these questions you're going to get, that is what we need to know. 2 on the innermost ring, 8 on each one else. And again, it's not necessarily true in real life. For the purposes of figuring out these questions I'm going to give you, that is what you need to know. Because the outermost ring is full, it is stable. What I just drew here is stable because it has 1, 2, 3, 4, 5, 6, 7, 8 on its outermost ring. So it is stable. This one is also stable because its outermost ring just happens to be the inner ring. It's not really an inner ring, right? It's just the first ring. But its outermost ring has 2, but it's full, so it is stable. That thing's stable, that thing's stable. So again, if it has a full outer ring, it's not going to have any bonds. However, a lot of times they do not have a full outer ring. Therefore, they have chemical bonds, chemical reactions that enable the atoms to transfer or share electrons because they want to get that outer ring filled any way they can. And that's what keeps atoms close together, is them trying to fill their outer ring. As far as we're concerned, in this 100 level class, that's the basic answer right there. That's what keeps molecules together, is because they want to fill their outer ring. And think about that too. We're not going to get this deep in for the exam, but again, think about what I was saying about things of the same charge repelling each other. On the outside of every electron, of every atom, is a bunch of electrons. So when we bring atoms together, that's got to be a pretty strong bond because they're trying to fill their outer ring, but also those electrons are still repelling each other. So those atoms, when you think about it that way, don't want to be together. So it takes energy to put those things together, even if they want to be together because they're trying to fill their outer ring. And the only reason that's important is because, like I said, this is going to come up later. However much energy it takes to build a molecule to squeeze those atoms together, That's how much energy would be released when you break those bonds. And that will be very important later in the semester. For now, just know that if they don't have a full outer ring, they're going to do what they need to do with other atoms to fill that outer ring. We call that the octet rule. Because again, the outermost ring, in our class anyway, has 8 electrons. Another thing you could look up for extra credit later, not now, right? Pay attention to the lecture later. What are the exceptions? Or, like I said, this one has 8. What's the next one have? What about the one after that? You can look that up if you want for extra credit. But again, for our purposes, it's 2 electrons on the inside, 8 on each ring. Any questions about that slide? Okay, so why is this relevant to biology? It's because cells are constantly rearranging molecules. They're breaking some down, they're building new ones. That is what life is. Without that, we would not be alive. Not just because we need those molecules, or when we break them, the parts of those molecules, but that action of breaking down molecules and releasing energy, that's the energy that keeps us alive. That's why we are alive right now. It's because right now, your cells are breaking down molecules and releasing that energy, and then they're putting that energy to work. That's why we're alive. So when we change these things, when we have these changes in the chemical composition of matter, we call that chemical reactions. That's the definition, the book definition of chemical reactions from the old textbook. It's like 99% chance I'm not going to ask you that. There's a let me rephrase that, because I don't remember for sure. There's a 99% chance that question's not already on exam 1. And if it is not on exam 1, I'm not going to add it. There's a 100% chance I'm not going to add it. So the point is, I really don't think I'm going to ask you the definition of chemical reactions. You need to know how they work, but I won't probably not going to ask you the definition. You do need to know this though, reactants and products. Hopefully their names kind of tell you what they are, and hopefully it's easy for you to remember. Reactants are the starting materials. They're the things that are going to be in the reaction. And products, obviously, are the product of the reaction. They're the end material. For this course, this isn't the way it is in all of chemistry, but for us, the reactants will always be on the left and the products will always be on the right. And the arrow will always point away from the reactants and to the products. It's not the way it is in real science or real chemistry, but for this 100 level course, it is. Another interesting thing about chemical reactions is a lot of them are reversible. So in real life, there might be an arrow there, but in all actuality, could have an arrow pointing both ways. But one thing you do need to know about chemical reactions, and this will be a little bit more important later in the semester, is that chemical reactions do not create or destroy matter. You might create or destroy molecules, like in this case, we have 2 hydrogen peroxide atoms to start with, but we destroy them, we break them down. So we've destroyed the hydrogen peroxide molecules, but we haven't destroyed the matter. See, it might be harder for you to see. But here on the left-hand side, we have 1, 2, 3, 4 oxygens. Here on the right-hand side, we have 1, 2, 3, 4 oxygens, right? Here on the left-hand side, we have 1, 2, 3, 4 hydrogens. Here on the right-hand side, we have 1, 2, 3, 4 hydrogens. So that we haven't created or destroyed any matter. We just rearranged it. Still have the same ingredients. That's just an example. I'm not going to ask you any questions about hydrogen peroxide. But I like that example because you guys are probably pretty familiar with it. How many of you have ever, fix that. Okay. How many of you have ever got cut or scratched or something and had to put hydrogen peroxide on it? Anybody? Yeah, what happens when you do it? It burns a little bit, sure. What else? What's it look like? Yeah, bubbles, right? And this is why. Not that it matters, but hopefully some chemistry I think is interesting. It's because when you put this on there, it breaks it down. And like she said, it's bubbles. And what are bubbles? Well, they're always something different, but liquid and air, right? In this case, water and oxygen. That's why it bubbles. It's because you're creating water and oxygen. Anyway, any questions about that? Okay, before we go to the next slide, I want to remind you again. If you change the number of protons, well, you tell me. If you change the number of protons, what do you get? See if anybody remembers. Change the number of protons, you get what? Like if I have a helium with 2 protons, if I take it away, what do I have? A different element, good. If you change the number of neutrons, what do you get? Very good, yes, isotope. That leads us to the third one. Change the number of electrons, you get something called an ion. Finally, we finished that discussion. Because remember, as far as we're concerned, there's only protons, electrons, and neutrons. So now you know, for the exam, what do you call it when you, or what happens when you change any of those numbers? Change the number of protons, you get a different element. Change the number of neutrons, you get an isotope. Change the number of electrons, you get an ion. I hate that also starts with an I though, because that can be a little bit confusing. Especially if you're if you get nervous taking your test, you might be like, oh my goodness, is it ion or isotope? Those things are very similar. But yeah, anyway, ions, electrically charged atoms. And they're electrically charged because you changed the number of electrons. You either took some away or you added some. And there's words for that. You might need to know this too. You definitely need to know that ions have a charge because they have, extra electrons or fewer electrons. But you might also need to know specifically which are which. For example, cations are positive because they have lost electrons. They have more protons than they have electrons. That's a cation. An anion is negative because it's gained electrons. So therefore it has more electrons than protons. I hate to say it this way, but this makes sense for a lot of people because I feel like I'm one of the few people who can't stand cats. If you love cats, it's an easy way for you to remember, right? Cats are a positive thing. Oh, it's my little fluffy pet. There you go. So therefore it's a positive thing. Cats are positive if you like cats. If you're really obsessed about ecosystems like I am, then you don't like cats because they're an invasive species, but that's a whole different story that we'll talk about later in the semester. So anyway, you know what ions are, you know the different types of ions. Obviously, when you put two ions together, we're going to call that an ionic bond. Because again, like we said earlier, these things want to have a full outer ring. So if they don't, in some cases, they're going to give up some electrons. Like, man, all I need to do is give up this one electron and I don't have a full outer ring. And the other one's like, hey, that's funny because all I need is one electron. And if I do get that, I'll have a full outer ring. And they're like, all right, let's exchange. And that's what the next slide is going to be, is a picture of what I just described. Are there any questions about this before I move forward? All right, good. Really quickly. It's a great example. And we've already talked about sodium chloride, right? Here we have sodium. You can see its outermost ring only has one electron. Chlorine, its outermost ring has 7. So sodium's like, all right, if I get rid of this one electron, then I'll be in my next ring, and my next ring is already full. Chlorine's like, man, I just need one electron and I'll be full. So again, they give it up, right? They help each other. Sodium's like, here, take my electron. And when that happens, obviously the sodium is going to become positive because it got rid of something negative. And the chlorine is going to become negative because it got something negative. Therefore, they're charged, right? Now this is a positive atom, a cation. This one's negative, an anion. And they're attracted to each other, right? Opposites attract, at least in chemistry. So that's what keeps them together. They're charged. They have, opposite charges, so they're attracted to each other. This will be really important later too, because later when we start talking about water and how it has partial charges and things like that can disrupt it. This is why water is really good at dissolving salt, because as you're going to learn later, again, water has a partial charge. One part's partially negative, one part's partially positive. So when you put salt in water, water is really good at breaking those ionic bonds up. But you'll learn that later. That's it. I guess the last word for attendance will be salt. And I will be in my office and online until 10 a.m. And then if you need me after that, I'll be more than happy to meet you online with my camera off because I'll be at home. But you don't have to do these labs or 3 labs alone. Let me help you. If you find yourself in a time crunch and like, oh my God, both of these things are due, prioritize the pre-lab. I'd rather you turn in the pre-lab or the lab late than the pre-lab. I want to make sure you're ready to go to lab next week. You've already done this lab. I'm less worried about that. Ooh, yes, yeah. We don't really get into it too much, but yeah, electrolytes are a lot. Yeah. It really is electric. Yeah.
Yeah, I wondered.
Appreciate it.